Log on, tune in, find out. Another good idea from Cambridge.
I think I switched on my, yeah, it's good. Okay. I'm really glad to be here. I want to tell you about this, really explain the title, the power and weakness of randomness when you're short on time. So it's basically a survey on some very basic results in computational complexity that have to do with understanding the power of randomness in computation. The plan of the talk is, it's rather dense. It's supposed to be a general talk, not for experts, so I'm going to explain some very basic things about computational complexity, like what are efficient algorithms, what are easy and hard problems, P versus NP, and then I'll start talking about randomness and this sort of schizophrenic view maybe we have of randomness, first about the power of randomness in algorithms, and then about the weakness of randomness, where it will, I'll really have to define what we mean. Randomness, of course, was studied, for millennia and used for millennia by people. I'll have to say what we mean by it formally when we look at things through computational complexity glasses. And at the end, if I have time, I'll talk about the same issues, but in different settings, the power of randomness in saving space as opposed to time, and in strengthening mathematical proofs. Okay, so since it's busy, let me start. But please stop me if there are questions. I mean, the timepiece, will do its job, and then we can stop earlier or have our reception food. Okay, so hard and easy problems. So we look at problems, the computational complexity of functions asymptotically as the size of data grows. Here's an example of an easy problem, what I want to call easy. That's a multiplication problem. You're given two integers. What's the product? How does it degrade with the size of the data? If you have n-digit inputs, at least the algorithm we were taught in third grade, it takes about quadratic number of steps. So quadratic is a polynomial. Polynomial time is what we call good, efficient. So this problem is in P, as a polynomial time algorithm. What's the sort of other side of the coin? Here's a problem that's very much related to multiplication. In fact, sort of the inverse. I give you an integer and ask you for the prime decomposition. The best algorithm we know today for this problem roughly runs in time exponential in square root n, where n is the number of digits. And that's, if this was the best algorithm, we would say that's a hard problem because it's exponential time as opposed to polynomial time. I think I have here water. So if that was, we don't know if that's the best algorithm, but if it was, we'd call it a hard problem. We don't know the true complexity. In fact, we don't know the true complexity of almost anything. But I just want to say that this particular problem, factoring problem, it's a subject for a different talk, but for this particular problem, you, all of you, really want to believe that it's hard because you are using it sort of a daily basis when you shop online. Anyway, let me show you another problem for whose complexity we don't know. Map coloring, that's a, again from third grade, maybe geography, atlases. You have these maps which are colored, but suppose I gave you a map which is not colored, and I ask you about coloring it. Coloring, I mean, of course, with two countries share a border, you want to give them different colors. And one reason to tell you about this problem just in general, when you talk about computational complexity, just showing that knowing the computational complexity of a problem is a difficult task because slight changes in the question change really the complexity a lot. So suppose I ask you, is such a map two-colorable? Can it be colored with just two colors? How difficult computationally is this problem? Well, this is really easy. More or less the greedy method, color the first by red, the neighbors by blue, the neighbors of these guys by red, and so on. Try to do it. If you succeed, fine. If you fail, no other way would have worked. So computationally, it's linear time, so it's in P. But when you change the question, I give you a map, is it three-colorable? Then this greedy method doesn't work. And in fact, we don't know of a good method other than more or less trying all possible colorings. But the number of possible colorings is 3 to the n, so that's exponential. We don't know a much better way. So that seems like a hard problem, but we don't know, as I mentioned. And then you change it slightly again, and I'm sure you all know what the answer to this one is. For this one, you know, it's the same type of question, but for this one, you don't even have to look at the input. The answer is always yes. So the complexity of computational problems, you know, vary drastically with slight changes to the question. So that's one reason it's hard. But anyway, let's talk about three coloring. Here's a theorem that if you never saw it, should surprise you, I think. You know, we don't know the complexity of three coloring, we don't know the complexity of factoring, but if we have a fast algorithm to three color maps, then we have a fast algorithm to factor. And that's an example of things we know in computational complexity that stems from the NP completeness of this problem, three coloring. And there are numerous problems like this. Again, it's subject for a different talk. But that's just for those people who want to remember the P versus NP as a, you know, when you want to ask, you know, your neighbor or your kid about it. The P versus NP question is basically just whether three coloring is easy. If three coloring is easy, has a fast algorithm, then P equals NP. Otherwise, P is different than NP. Of course, it captures a lot more, and I won't say much about this in this talk. Okay, so we talked about computational complexity. There are P versus NP questions. There are lots of problems for which it seems that the best algorithm... Question? No? Yes? No. There are lots of problems for which we don't know the answer, but the best algorithm we have is exponential time. And it seems, you know, like all these problems from very different areas, the best algorithms we know are exponential time, or if we build circuits for them, it's exponential size. And the question is it the best? Can we do better, or, you know, are we forced to sometimes pay exponential time for these problems? And, you know, I think by far all experts agree, you know, that the answer should be yes. So that's a belief I want you to remember. Okay, so that we believe that. I didn't say anything about randomness so far, so let's go back to randomness. And I want to talk first about the power of randomness. And to demonstrate the power is very easy. I'll just give you a bunch of problems, mathematical algorithmic problems, for which we have a fast probabilistic algorithm for solving it, but without randomness in the algorithm, we just you have no better way than sort of brute force exponential time. So I just want to give you a bunch of examples like this. But before I do, let me just say what I mean by a probabilistic algorithm and when do we, you know, call an algorithm good. So algorithms from this point on are allowed to toss coins in order to make decisions. Toss coins, I mean just independent, unbiased coin tosses. The uniform distribution, basically. And for any task such an algorithm is supposed to solve, we want that it will succeed with very high probability, let's say 0.99. Okay? Otherwise, you know, we don't want to use it. But if it does with very high probability, like 0.99, then we accept it. So these are the kind of algorithms we are considering now. It seems like, I mean, I think most of this audience is, you know, knows that why probabilistic algorithms are used. But let me just say, spend a minute on it. Why should we even tolerate errors in algorithms? I mean, if we want to solve a problem, we want to know the answer for sure. Well, there are many answers to this question. I think maybe the best one is we tolerate uncertainty in so many aspects of life, and might as well tolerate it in the Like you cross the street and you know, it's not 100% you'll get to the other side, especially in England when the cars are coming from. In fact, errors in probabilistic algorithms are much better behaved than in normal life because you can reduce them. You can make them as small as you want just by repetition. You can make them exponentially small, so that's great. And of course, the real reason we use probabilistic algorithms with errors is because it seems we can do much more with them. Okay, so let's see examples of this. So I have 4 examples from 4 sort of different disciplines. First, number theoretics, so recognizing primes. In fact, the prime example of the power of randomness was taken away from us a few years ago, but I'll tell you about this and then, you know, make a variant. So here's a basic problem. I give you an integer, an n-digit integer, and ask you whether it's prime. That's a computational problem. What's the complexity? In fact, a result that started the field of probabilistic algorithms, at least within computer science, was this result by Solveig-Strassen and shortly after Rabin, showing that this can be done very fast if you can toss coins. And for a long time, this was the example. We said, look, we can do it randomly, but not deterministically, until a few years ago, where these guys came along and found an efficient algorithm, polynomial time algorithm, which is deterministic and polynomial time. But not to worry. Suppose we change the problem a little bit, and I now just give you n, the size, 1,000. I give you 1,000. I ask you, give me a 1,000-digit prime. What's the complexity of this as a function of 1,000? And of course, probabilistically is no problem. We pick some random numbers of this length. We pick a linear number of them. Then one of them will surely be prime, right? Or with very, very high probability, just because that's the density of primes. Primes are dense in the integers. And of course, once we, you know, one of them is prime, we can check either deterministically or probabilistically that it's a prime. So this probabilistic algorithm will generate a prime with very high probability. But if we try to do it deterministically, the best known way takes exponential time. So here's a problem where it can be done in polynomial time with randomness, but seems to require exponential time without randomness.
Is it true that given the Riemann hypothesis, if you just pick them sequentially, you'll find one pretty fast?
You need something stronger than the Riemann hypothesis. You need that there are primes within, let's say, polylogarithmic range. So there are number theoretic conjectures which will make this have a polynomial time solution. But I think it's stronger than the Riemann hypothesis. Yeah. Yeah. But anyways, this is not known whether this can be done deterministically, and we don't know whether the Riemann hypothesis is true. So as far as we currently stand, there seems to be an exponential gap between these two.
You'll have to prepare new slides in a few years, maybe.
Maybe, yeah. You're working on it. Okay, here's a completely different problem. You may recognize this matrix, the van der Monde matrix, and indeterminates, and you know this famous matrix. And I can ask you whether the determinant of this matrix is identically equal to this polynomial, whether the difference is identically 0 polynomial. What's the answer?
Yes.
Yes, very good. Now, that's van der Monde's theorem. In fact, it's a pretty easy theorem. We give it as exercise to undergraduates. And but the more basic question is, how did he know? Okay, I mean, maybe this is not so difficult to know, but I give you another conjectured algebraic identity. How do you know that it's true? How do you know even if to start working on it? So what do I mean given an identity? I just give you a multivariate polynomial in some concrete description like determinant or a formula for a polynomial in n variables, let's say of some degree d. And I ask you, is it identically 0? That's an algebraic identity. That's the kind of thing that sometimes people work for years to prove and, you know, succeed or not. What, you know, how would you know whether this is true, whether what you want to prove is? So here's a very simple algorithm, Schwarz-Zippel algorithm. Says, well, at least you can get huge confidence that what you're trying to prove is true just by plugging in random numbers into the indeterminates, into the variables. Plug random integers, if it's degree d, plug random integers, let's say between 1 and 100d, to every variable independently. Okay, and now you can evaluate because you have a formula for the polynomial, so just evaluate it. Maybe I should stress, there is no way to test this equals to 0 just by expanding the polynomial and checking that all coefficients are 0, because there are exponentially many, so in many variables. So what happens when you plug in random values? Well, if the polynomial is 0, of course, each time you plug in something, you'll get a 0. That's good. And it turns out that if it's not 0, of course, you understand. If it's not 0, then the variety has measured 0 in space. But in fact, even for integers, it's very unlikely that you will hit the variety. Okay, and so with very high probability, it will come up non-zero, and you'll know. It's a very simple probabilistic algorithm. The analysis is simple, and as far as we know today, there's no better way deterministically than just trying, exponentially many possibilities, or just exponential time algorithm, checking all coefficients. This, by the way, is very important for lots of other reasons, and it's, there are generalizations of it. You can actually, in probabilistic polynomial time, factor multivariate polynomials that are given in this form and so on. So it's a very basic result. So again, we have this exponential gap, at least as far as we know. Here's another very different for the analysts here. This is Cambridge, analysis, I'm sure. Fourier coefficient. So what do we want to do with Fourier here? Suppose I give you a function, let's say on the Boolean cube. Think of it as a abelian group, f2 to the n. And again, I give it to you implicitly as a formula or a circuit, something that computes it. And I give some threshold, epsilon. And the question is, find all the high Fourier coefficients. So it has 2 to the n Fourier coefficients, characters, and just find those that the function correlates with at least epsilon. Notice that even though there are exponentially many Fourier coefficients, they are at most just by Parseval, there are few that have such correlations, most 1 in epsilon squared. So if epsilon is 100, you will get at most 10,000 answers. So at least the output size is not going to be big. So how do you find this? Of course, you cannot compute all Fourier coefficients and just check which is large, because it's exponentially many. Well, here we already got into the realm of sophisticated algorithms. And there is a beautiful algorithm by Goldratt and Levin, which has sampling in it, but sort of adaptive and clever. And I'm not going to show it to you. But it gets all the high Fourier coefficients with very high probability. And in fact, it was extended to all abelian groups. You can do it for other abelian groups. And that's one of the most useful algorithms we have in computational complexity. It's related to all this game theory and learning and these decodable codes and lots of other things that were generalized from that point on. But anyway, saying, sort of repeating myself, the best deterministic algorithm for this problem known is exponential time. And again, we have this huge gap. My last example is geometric. It's about estimating the volume of convex bodies. So here you are given a description of a convex body in high-dimensional space. Let's say it's a polytope, so you are given the bounding hyperplanes. And the question is, estimate the volume of this body, K. So why do I say estimate? Because computing exactly volume in this setting is sharply complete. It's something harder than NP complete, so we can't get it exactly. But maybe we can get it within a factor of 2. Okay? So estimate this volume. And here again, there's a very, very clever probabilistic algorithms, which, let me tell you a few words about it. You want to estimate it, so estimating the volume might as well put a fine grid in space and try to estimate the number of points. This algorithm, by the way, is a Dyer-Friesen-Cannon. So you want to estimate, but again, you can't count because in high dimensions there are exponentially many points there. So how do you find out or approximate? Turns out that to approximately count the number of points, it turns out to be sufficient to, almost equivalent, to just generate one point inside which is very close to uniformly random in that set. Of course, the set is sort of problematic. It's not like a cube. It's an arbitrary convex body. And how do you, so anyway, that you reduce it to the problem of sampling. This is, by the way, a result of Jerome, Vazirani, and Vazirani, this connection. And then you, to generate a uniformly random point, or nearly so, you just take a random walk in this. So you just start somewhere and start walking randomly to nearest neighbors in your grid. And of course, if you step out, you immediately come back in. So that's sort of the metropolis algorithm, which is easily seen to converge eventually to the limiting distribution, which is uniform on this point. The question is just how long it takes. And it turns out that this, by analysis, you have to analyze spectral gap of this chain, and you find out that it converges in polynomial time. So it's again a probabilistic polynomial time algorithm that does what it should with very high probability and also solve the counting problem. And it's a very applicable, I mean, it's related to lots of algorithms of this nature, what's called MCMC, Markov chain Monte Carlo algorithms. So there are lots of other examples I could have given you of this nature. And again, in all of them, there is a fast probabilistic algorithm, and as far as we know, best deterministic algorithm takes exponential time. So by now, you should be sold on the idea that when I ask you, does randomness help? What do you say? Yes. Yeah. So other problems, like the 4 ones I've shown you, where probabilistic does much faster than deterministic by more than polynomial amount. That would be the natural conjecture. Let me remind you the first conjecture. It was a conjecture that NP or problems of the sort I've, like free coloring or satisfiability or traveling salesman or finding optimal strategies in even harder problems than NP, let's say in chess, stuff like that. Some of them require exponential time, exponential size. That was also yes. So, okay, good. So you've seen now 2 very basic questions in computational complexity, maybe the most basic questions in computational complexity. You've seen what is natural conjecture for each, and the question is why are they on the same slide? What do they have to do with each other? And that's the reason. We can prove at least that they are connected. So one of these conjectures is false. I can tell you even which one, but you'll see it anyway. Yeah, it's this one. Okay. So I want to explain this connection. That's the main task of the talk. I want to explain this connection, and this connection is the connection between, hardness and randomness. Okay. So that's a connection. And actually, this understanding we came about, over a series of works, starting in the mid-80s. Started really from cryptographic motivations, or even early 80s. Intuitively speaking, this is the meaning. I'll be more concrete. But if there are natural problems that are difficult to solve, then randomness can be eliminated at essentially no cost up to polynomials. That's the message. Okay, and more concretely, one of the theorems, there are several of them that maybe is the strongest we know. We did with Impagliazzo some decade ago. If NP, and again, you can put even larger classes here. If there are some problems, let's say in NP, which require exponential size circuits, then every probabilistic algorithm, which is efficient, like the 4 ones I've shown you, these and any other one can, has a deterministic counterpart, can be replaced with another algorithm that runs also in polynomial time. So you can eliminate the randomness from every efficient probabilistic algorithm if any one problem is exponentially hard. Okay, so that's the message. Okay. I just want to say, I will not talk about it here, but now that there is a connection, there is a one-way connection between hardness and randomness. If you have hardness, you can eliminate randomness. It turns out this connection is even deeper than you might think, and it sort of goes the other way also. In some sense, we don't have anything tight yet. But there are some works that tell us some partial converse, but I will not talk about this here. Okay, so I want to explain this connection. So I want to demystify this thing. Okay, so let me...
But what do you mean converse? That if you can prove that...
if you can de-randomize something, then you can prove lower bounds. Yeah. In some contexts and some type of models, yes.
And
yes.
Also this talks about circuits.
This talks about circuits, and there are results that we can prove also for in the uniform model, which are weaker and will require more definition, so I'm stating. Yes. Right. Okay, so I'm going to prove this theorem. Well, I'll give you main ideas, highlights from the proof of this theorem that hopefully will convince you that there is a connection. You can fill in the details if you really want to. So again, we want to assume that there is a hard function, and we want to show that this implies that we can take any probabilistic algorithm and remove the randomness from it, do it deterministically without losing more than a polynomial amount of time. Okay. So the first thing you wonder, okay, maybe for algorithms that were already invented, like the 4 ones we've seen, we can, look at it and say, oh, I can, remove the randomness from it. But what do we do about these probabilistic algorithms that were not even invented yet? How do we remove the randomness from them? So we have to have some general, approach to this type of algorithm. So what is a probabilistic algorithm? Here is a generic probabilistic algorithm. It takes some input, and it takes a bunch of independent, unbiased coin tosses, which, let's say, n of them, which I denote by like gold, mint gold coins. And when they are fed here, with very high probability, the output is the correct one. Right? So that's a generic probabilistic algorithm. And we want to eliminate the randomness. Somehow we want to run this without the coins. Okay, that's the task. For any such algorithm, as long as it is efficient. That's the only requirement. So how can we do that? I mean, how can we even talk about this? And it turns out the absolutely key idea is to not just think about removing them, but just think about plugging in, instead of this uniform distribution, just a thought experiment. What happens if we plug a different distribution there? Just try to understand the behavior of this algorithm under other distributions. Okay, maybe with less entropy, eventually zero entropy, but with less entropy. So we want to study this situation where there's a bunch of antique coins here that may be biased and dependent, some arbitrary distribution. And this is a really key insight, because then you can make a definition. And the definition, which was made by Goldwasser and Micali, is to talk about which distributions here would be good enough. Which would be good enough? These distributions, so call a distribution pseudo-random. It's a definition, it's a key definition. A distribution, let's say on n bits, is pseudo-random if it fools any such algorithm. So again, it's pseudo-random if for every efficient algorithm and for every input, you get the same distribution on outputs up to epsilon, let's say up to 1%. Let's say this algorithm is supposed to say yes or no, then we know the original algorithm is supposed to succeed with probability 99%. We don't mind that this will succeed with probability 98%. Okay? But this distribution should fool every algorithm which is efficient on every input. At this point, it's just a definition. It may be a wishful thinking, Maybe the only distributions we do this are distribution with entropy very close to n, and then, so it's okay, so it's a definition. And what we would like to do, certainly if we could generate such a distribution without any entropy, then we will be fine. Because we don't really need this distribution. We need any pseudo-random distribution. So that's a major leap. So let's try to generate it. What does it mean, generate it? We want to start with no random bits and deterministically generate such a distribution. That's our goal. Of course, you cannot generate any entropy deterministically. So we want to do it deterministically and efficiently. This is sort of impossible, but in fact, we don't have to start with nothing. We can start with very few random bits, truly random bits. We can assume we have about logarithmic number of them. Why? Because eventually, if you had a randomized algorithm that worked with just log n random bits, you can just try all possibilities and do a majority vote. So in some sense, that's for free. So what we want to do is deterministically and efficiently take about logarithmic number of coins, which are genuinely great, independent, unbiased, and generate from them a pseudo-random distribution. That's the hope. And if we can do this, then this will be called a pseudo-random generator. So far so good. We haven't used the assumption that we have a hard function, and I didn't explain you how we can convert a hard function to such a generator. But that's basically what's going to happen. Okay, so let me tell you about two parts of the proof that are key. And the first one, so how do we convert hardness to pseudo-randomness? So we want to stretch k bits, k was this log n, into n bits. What I'm going to show you is something much easier, how to stretch k bits, whatever they are, into k plus 1 bits. So how to get just one extra coin toss deterministically, so that it looks random to every efficient algorithm. And then if you can do that, if you can just get one more, it's just, I keep telling this, just somehow I was very influenced when I was a kid, when I heard that to become a millionaire, you just have to get the first million, and after that, all the other millions are easy. I still don't know if it's true. But at least in this setting, it's true. So there is this gadget called the NW generator that we developed with Noam Nissan, and if you can get one more, then you can get many more, exponentially more. So let me tell you how this is done. And in fact, once you get here, it's also almost forced on you. So you want to generate from k bits, k plus 1 bits that look random to any polynomial time, polynomial in n, remember, and k is log n. So to exponential time algorithm in k. Well, you have k bits, you want k plus 1. Well, for free, you get k of them, so let's just send them there. And we just want to get the last one, so it will be sort of unpredictable from the previous ones. What can we do? The only thing we can do deterministically is just apply some function on them. Which function shall we take? We'll take our hard function. That's where hardness comes in. So at this point, once we reach with all these ideas aligned, it seems like we have almost no choice. Of course, there's a lot of complications I'm hiding. In particular, this hardness, I mean, what do we want? We want that on a random input, this bit looks like, 50-50. So that's not the hardness we talked about before. The kind of hardness saying that, free coloring is hard means that, maybe almost all maps are really easy to free color or to decide free coloring for them. Only very few of them are hard. Here we are talking about very strong average case hardness. And so you have to, another part of the proof has to do with this hardness amplification. It turns out that you can start with a function that's hard even very rarely on some very few inputs and convert it into a problem that's hard, you cannot tell apart the output from a coin toss. That's another thing that has to go into the proof. But So with these pieces, you fill in the proof. So I just want to run through the general, how are we, once we are done with that, how do we remove the randomness from a generic probabilistic algorithm? Well, we take it. This is the algorithm we have. We are given some input to it. And what we are going to do is, I described to you in, very, very high level, a pseudo-random number generator that takes a logarithmic number of perfect coins, converts them to a pseudo-random distribution, and then we just deterministically try all 2 to the k possibilities, which is just polynomial in n. For each of them, we run the generator, get a sequence, run the algorithm, ask it what the result is, and we have many results. Just take a majority vote. Why does it work? Because, the probability of success was 98% maybe instead of 99, but a majority vote is certainly good enough. So no, there is no error in this deterministic algorithm. You get something even better than you started with. Okay, so that's the proof, and that's the way to convert probabilistic to deterministic algorithms. I want to say something about this connection. So there's this connection between hardness and randomness that we were using here. In this general setting, it worked under an assumption. It worked if you had a hard function. But in fact, for many specific algorithms, so you can ask, if you have a specific algorithm like the ones I showed you, can I fool this algorithm, just this algorithm? Can I build a pseudo-random generator to fool just this algorithm? Maybe for this I don't need assumptions. And it turns out this is a very powerful paradigm. It works in some cases, and very important one is the primality testing I mentioned, algorithm I mentioned earlier of Agarwal, Kayal, and Saxena. I'm sure many people heard of this breakthrough that they found a efficient deterministic algorithm to test primality. I'm not sure how many people realize that it was done using this. They designed their own favorite probabilistic algorithm that was different than previous ones, and then they went on to build a pseudo-random generator for it. That's exactly what they did. And that's, that was the randomization. Primality testing, and there's another one I'll show you in a minute. Yeah. Questions about this? Everybody understood it.
Can I be certain that, a naive question, can I be certain that in, as it were, scaling up to n, you don't introduce coefficients which somehow, are hit you hard in the actual competition?
No, definitely not. No, there is no. It's a combinatorial setting, and there are no. It's completely combinatorial, and you don't introduce any. The analysis of the running time does not depend on any hidden assumption, just on the hardness of the function you are using. Yeah.
So in real life, we use pseudo-randomness even before this proof. So this is just to make it provable. So in real life, we use randomized algorithm, we use pseudo-randomness, and we have some extra uncertainty.
Yeah, so in real life, it's not clear. It really seems in real life, you say maybe the conjecture that randomness is powerful is this conjecture that it is powerful. So that proves that it's not powerful. But,
right.
But what you're saying, maybe we knew it because anyway we are using various deterministic sequences in the probabilistic algorithms. Of course, this does not prove that the digits of pi are good. They don't prove that, taking keystrokes or whatever is used in the computer, some simple linear congruential generators are good. It doesn't prove that. But it's sort of, you're saying it adds theoretical...
yeah, we cannot prove everything, but it's add to our intuition anyway.
So I think that that the two are not completely related. So maybe this is really a connection between hardness, between computational difficulty and pseudo-randomness. I'm not sure that explains pragmatic success of various other things that are used. I'm not sure it's an explanation. Maybe, there are many ways to randomize probabilistic algorithm. So, but that's the only one that's provable, and it needs an assumption. No question? Okay. Let me tell you about the power of randomness in another setting. Until now, we are trying to, save on time. Let's try to save on space. So here are, two settings, just to show you that, exploring, navigating unknown terrains is, a very old and very new problem. And what I mean by that is basically that you find yourself in some town you don't know, maybe Cambridge, and you have to find your hotel. Cambridge is actually too small. You should think London. And you want to find your hotel, and you don't have a map. And moreover, you don't have the space to write them. Of course, you can just start to explore the city and draw a map. But all you have is a local view. You just can remember roughly the street names at the intersection you are at. That's the memory you have. So can you find your hotel in this setting? And I'm sure many people heard me saying this a long time. Here's the right way to do this, which was suggested by this beautiful algorithm 30 years ago. What you should do is just take a random walk in the city, or as other people prefer to say it, go into a bar, have a few beers, and start looking for your hotel. So what they showed is basically this random walk approach. You don't have to remember anything for it, right? You just randomly walk. Is that they showed that in polynomial time, you will hit with very high probability you'll get to your hotel. If n is the number of intersections in this graph, then with very high probability you get to your hotel, and in fact, not only to your hotel, but to every other hotel in town. So you will completely exhaust the connected component in the graph you live in.
No assumptions about the graph.
No assumption. Any undirected graph, no one-way streets. If you are driving, maybe different. Yeah. If you are driving drunk, anyway, you shouldn't be doing it so drunk. Okay, so it was open for many, many years, for 30 or 25 years, whether one can de-randomize this algorithm. So you are asking about doing this kind of thing without randomness or without Beer. And just a few years ago, Omer Reingold managed to do this the phenomenal result. And what he's providing you with is basically a deterministic walk, a way to explore the city or any city in small space. So you don't have to remember much more than the size of a street corner as opposed to the size of the city, log n space. And here the de-randomization, so it's another de-randomization result, it's a pseudo-random generator for this kind of model. And it's very different than what you've seen before. It doesn't use any assumption, first of all, it works. And the pseudo-random generator depends on what's called the zigzag product on expanders, which we developed a few years earlier that I will not be able to talk about here. But anyway, that's another pseudo-randomness result, and it seems that in this setting where you don't have one-way streets, it's doable, and there are open questions there about when you do have one-way streets. Yes. In regular graphs and but if you want. I just want to say polynomial time. Yeah, you're right in general, yes. Okay, so the last setting I want to talk about is the power of randomness, and here it's really the power, as opposed to maybe before it was the weakness. As I type randomly on my...
it's a Greek row.
It's a row, yes, very good. Okay, I hope you can understand this.
It's an error correcting code.
Let's get rid of this slide quickly. So I want to talk about proofs. And I want to explain what probabilistic proof systems are. And this was introduced in these two independent papers in the mid-80s. So to tell you what probabilistic proof systems are, let me tell you first what deterministic proof systems are, and in a very general way. So what are proof systems for? It's for proving theorems, right? For proving various claims in mathematics. And a proof system is basically defined completely by a verification procedure. So you may remember logic books with lots of, quantifiers, forget it. All of them fall into this category, right? All of them can be described as follows. There is a verification procedure, V, which is efficient. It's always efficient. It's always key for proof system that the verification of proofs is efficient. Otherwise, it's useless. It takes two inputs, a claim and an argument, and it should satisfy the obvious completeness and soundness conditions, right? If the claim is true, then there must be some argument which convinces the verifier to accept. There's a happy case where we call the claim a theorem and we call the argument a proof. And if the claim is false, then no argument should convince this verifier. Right? That's a proof system, a complete and sound proof system. What's a probabilistic proof system? Well, like before, we had algorithms and we endowed them with the ability to toss coins. Here we have an algorithm, the verifier. Let's allow it to toss coins. That's a probabilistic proof system. Of course, we have to say where we allow error. And let's say that in this case, completeness, we just want if the claim is true, we want that there exists an algorithm, an argument which convinces V with probability 1. But if the claim is false, we allow some slackness, namely the probability that any argument will convince the verifier is at most 1%, even though the claim is false, right? We don't want this to happen. We say it happens with very low probability. And I want to stress that this probability is over the coin tosses of the verifier V. Does not, you can reduce it to exponentially small if he repeats and so on. So it's just the coin tosses of the verifier. Anyway, that's a definition. So you mathematicians among the audience say, well, maybe errors are understood in algorithms. Why should we care about errors in, for proofs? I mean, proofs should be definitely errorless. We want to know whether the Riemann hypothesis is true or not. Right? But I claim that, let's not get into mathematical theorems like the Riemann hypothesis, but there are statements that you yourself prove every day, again, in the cryptographic setting, like you prove to your computer that you know your password, and you prove to you prove that you own your credit card and stuff like that. In other words, there are lots of proofs going around all the time in cyberspace, for which having 1 in a billion error is not so bad. Okay. And if you prefer, think about these ones. But actually, we'll also be talking about proving mathematical proofs. So it's good for all of them. That's a probabilistic proof system. And I want to tell you when does randomness in proof system help with compared to deterministic proof systems. And now these will be dichotomies. There will be things that you cannot do deterministically. Okay, so I want to tell you about two settings in the last 8 minutes I have. Where is this thing? Oh no, seems like seems like at least 8.5 minutes. So two remarkable properties of probabilistic proof systems. So one is the setting of probabilistically checkable proofs, and the other is the setting of zero knowledge proofs. So I'll explain them both with one slide each. So what are probabilistically checkable proofs? The setting is, well, you have some claim, like the Riemann hypothesis. We have a prover, which maybe has an argument. And the verifier wants to check it. That's what the verifiers do. You can think of yourself as a referee of a paper that was just, given to you to handle. You just want to know that it's correct. Okay. This is takes a concern that's very dear to everybody here. We don't want to referee papers. If we do, we want to do it quickly. So what are PCPs? These are proof systems in which the verifier, you get the paper from the editor and it tells you, don't worry, just read 100 bits and decide whether it's correct. we would really like this kind of request. So what can you prove about the answer you give after you read it? That's the question. So,
No, but this journal has very special submission requirements.
of course. So yes. Okay, so let me say for those who don't. So that seems totally ridiculous, right? I mean, what kind of value can a verifier who looks only at 100 bits of a 100-page proof be? I mean, what's the chance of catching a bug? Well, it turns out that it's not ridiculous at all, this proof system. And in fact, in this very celebrated, it's actually 2 papers from about 20 years ago, show that every proof can be efficiently transformed into another proof, not much longer. It can be in polynomial time transformed to a PCP, namely to a proof that can be verified just by reading 100 random bits. And I repeat, it will have the property I said before. If the claim was true and the argument was correct, the verifier will accept reading 100 bits. And if the claim was false, then the verifier will catch a bug just by reading 100 random bits. Okay? So such is the format that this PCP has. It sometimes they are called holographic proofs. It's a very deep theorem, converting a proof to a holographic proof. And, but once you do it, somehow bugs, if they existed at all, are spread everywhere. So that's a major result. Of course, its application is not in refereeing, but actually it really caused a major development within complexity theory and optimization, and it's mainly used in determining the exact approximation ratio you can get for a lot of optimization problems. So we really understand it very well today due to this result and subsequent results refining it. So that's PCPs. Okay. Of course, deterministically, if you read 100 bits, so if you are telling me you read the first 100 bits, certainly I can make sure the bug is somewhere else.
This efficient transformation actually verify the proof.
No.
It doesn't?
No, it doesn't. No, it can be done whether it has a bug. The efficient transformation is done sort of oblivious.
But it's easier than it's harder than to verify the proof automatically.
Once you have done this, you can.
So once the proof is in a format that you can make this transformation, you can also verify it.
No, it's not the proof is in a format that you can do the transformation. You can do this transformation to any proof. You can take any proof or any argument. It doesn't.
Any proof which is written in a formal way that you can, in any case, verify.
In any case, verify by reading it all. We don't want to read it all.
But this transformation is done by a computer because it's.
So we can get into the practical value of this. I already said it's not used for practical. Yeah. So if you want, I will not claim it's practical. It has huge theoretical value, but it can have. I don't dismiss the possibility that it will have practical value, not necessarily for the Riemann hypothesis. Okay, so that's one thing you can do with randomness. You can reduce the time of reading a proof from linear to verifying a proof from linear to constant. The other setting is the notion of zero knowledge proofs, which was introduced in the same paper I mentioned before that introduced probabilistic proof systems. So the setting in some sense is the same. We have some mathematical claim, we have some prover who may have a proof, and the verifier who wants to check it. But now the concern is not how much time the verifier spends, but rather the paranoia of the prover. Okay, what paranoia can the prover have? Well, you send the paper to a journal, maybe the editor, or maybe you tell it to a colleague. I don't want to cause concern here. It rarely happened in the history of mathematics that this, rarely, but it did happen. So how can you address such a concern that you want to boast your proof of, let's say, really Riemann hypothesis, but you don't want you want to protect your authorship, your rights. So zero knowledge proofs allow you to do it. Zero knowledge proofs are a mechanism that by which you can convince somebody else that you have a proof of the Riemann hypothesis without giving them a shred of information about your proof. And nevertheless be completely convincing. So this seems, even more ridiculous than the previous one. But the previous one you saw that was really not ridiculous, and neither is this, because we proved that every proof can be converted efficiently into a zero knowledge proof. So if you have a proof, you can use this mechanism and convince your colleagues that you have it without revealing anything about your proof or about anything else, about your private life in the process. There is a difference in this one than the previous one, is that here we have an assumption. The assumption is something like factoring is hard, or we have one-way functions. So there is a computational assumption that goes in. It's basically the assumption underlying all of cryptography.
You cannot use it for a proof of a polynomial time algorithm for factoring.
So maybe you don't have such an algorithm, huh? Yeah. In general, you cannot have it for a claim that you cannot, that in particular is false, or you cannot have. But the assumption here, the computational assumption, can be a little different than factoring. So you can use lattices to prove. Anyway, that's another thing you can do with randomness. Again, of course, deterministically it's sort of meaningless, and and is impossible. Okay, so let me sum up, because I think very good. So I think what maybe a good way to sum up this talk is that I was focused on randomness. That was the title of the lecture, and the randomness through computational complexity eyes. And you could see that there are things that, from this point of view, you can say about randomness that other disciplines that were looking at randomness did not talk about. There comes out a notion of randomness that's not evident without computational restrictions. That is, in fact, very useful. I just want to point out that the same happens if you look at other sort of major notions like knowledge and proof, actually, and learning, and many others. When you view them from, computationally restricted eyes, then they acquire sometimes new and important meanings, both practical and theoretical. For randomness specifically, we saw that it was sort of in the eyes of the beholder. So somehow things are as random as the computational power of the guy or the algorithm looking at them. So all we needed to fool, for example, in the first part of the talk, were algorithms that were efficient. The pseudo-random generators generated distributions that, of course, could be told apart from uniform distributions if there was enough time. Of course, they don't have enough time. They are efficient. Therefore, they are fooled. And therefore, we can make them deterministic. And hardness was key in order to generate this good enough pseudo-randomness. And I mentioned that sometimes you so the consequence of this is that probabilistic algorithms are probably not as powerful as they seem to be. And in some cases, we don't need assumptions in order to de-randomize algorithms, some very important cases. And some other settings, like the proof setting, randomness is essential to achieve extra properties that you cannot achieve deterministically. Of course, there were lots of assumptions in various places. It's factoring hard. So basically, the computational complexity questions that are needed for this, namely hardness, are open. We don't know if factoring is hard. We don't know if P is different than NP. So these are my open questions for you. Thank you.
What a delightful talk. Any questions or comments to Avi?
Yes.
Yeah,
one thing I always find a bit confusing in this is that you take a randomized algorithm and you de-randomize it, but you still have a chance of error. So it's not quite deterministic in the same, or to me it doesn't appear to be deterministic in quite the same sense. How does that work?
I said there is no error in the deterministic algorithm. There is no error. Yeah, so it is deterministic in the usual sense. It's a deterministic algorithm. Let me explain again. Here was the algorithm. Here was the input. And here was supposed to be a random sequence fed here, so that if it was fed here, you got 99% success in the probabilistic algorithm. That's in the case that it was really random. So here there was error. In your probabilistic algorithm, there was error. But we replaced this algorithm because anyway, we don't have this thing. Instead, we replace it with the following gadget. There was a deterministic process here, this generator, a deterministic process that converted a few bits to many bits. Okay? And the way we run this whole process, let me just say the property. If these are random, just it's very few bits are random. If they are, then what you get here is slightly worse error, like 98%. Okay, so far so good. This is still a probabilistic algorithm with much fewer bits that has the same, basically, successful bits. And now the way you make it deterministic and errorless is try all possibilities of this. Okay? You try all, it's log n, so it's k, let's say c log n. You try all 2 to the k possibilities, which is just polynomial. You try them all. What do you do with each? With each, you run the algorithm with this sequence. And you know that 98% of these sequences will give you the correct answer. So if you take a majority vote, you get the right answer with no error. Okay?
You can even just try 5% of the...
If you want, that it will not save you much. Yes?
Yeah.
Yes?
You said that in this probabilistically checkable proofs, you can reduce the effort of verifier from linear
to constant. Yes.
But how much does the transcription take? Is it
So,
linear?
No, it's polynomial and it's a big polynomial. However, you may hope that this is done automatically, right? So in fact, you can, once you write your proof, conversion, it will not be done by you, but by some. But in fact, there is an efficient algorithm that will do it. So you don't have to.
Automatize.
Yeah, automate. Yeah, that's a very simple. Yeah. Yes.
What's the complexity of that generating function from the random seed to the random?
Polynomial.
Can you repeat
that? Yeah. So sorry. Yeah. The question was, what's the complexity of G? What's the complexity of G? So if you need to generate n bits. And this, so the two parameters that come in is n and the running time of this algorithm, t. Okay? You need to generate n bits against an algorithm that running time t, let's say polynomial in n. The complexity of this generator will be polynomial in these two parameters. What polynomial, you ask? Maybe, power 10.
So why does that not contradict? I mean, well, why doesn't that not give a proof of P equals NP? Wait, how does that?
It says no. Wait. We didn't do anything to NP, so I don't know why you ask about P versus NP. So let me just, maybe some things are unclear. This problem, originally, before we started with anything, it was a problem that already had a fast probabilistic algorithm. It's not an NP. It's not a it's not a general NP problem. It's a problem for which we have an efficient algorithm. Only it's probabilistic.
But you could have an NP problem that.
I don't know I mean, if it was an NP problem, an NP problem is a problem where there exists some sequence here that convinces the algorithm to do the right thing. There exists, as opposed to 99% of the strings do the right thing. There's a big difference between problems in NP and problems in what we call RP, random polynomial time. Right? Problems in NP, in general, we don't think there's an efficient algorithm, randomized or deterministic, to do them. Right? Here we start with something for which we have a fast probabilistic algorithm, and all we want to say is get rid of the randomness. Okay? Yeah.
In the answer to Keith's question, you have a deterministic algorithm, but you only know that it really works if under the assumption that you may wake up one morning and discover that it doesn't work, and the reason it doesn't work is because you were assuming that P is different from NP.
This would be fantastic. So let me repeat what Ehud is saying, or rephrase it so that conveys the message. You had the message. Here's what you can do. You believe that some function is hard, like let's say some NP-complete problems, it's viability or troubling salesman. I don't know what your favorite is over the permanent function. One of the functions for which the theorem works, right? Just build a generator. The generator is prescribed. Given a function, it gives you a generator. You can use it, and you can take it and use any probabilistic algorithm with this, make it deterministic using this presumed hard function. And now suppose suddenly you find out that it gives the wrong answer. What did you do? You prove the lower bound. You prove that, you prove the, not the lower, you prove the upper bound. You prove a hugely surprising upper bound. You found a way to do a problem we thought was exponentially hard in sub-exponential time. That would be major. So that's one way to do this. Of course, I'm not sure that's recommended, but that's one way to do it.
Well, we can continue informally outside of the reception. Everyone is invited to that, but can we thank Avi again for it?